for taking the time to attend. Like Kelly mentioned, we're going to walk through the steps that it takes to replace an optical encoder with a magnetic solution. And the idea is to save, again, like Kelly mentioned, some cost, actually a significant amount of cost, space, and increase functionality and reliability. So with that being said, I'll go over the quick agenda. We'll start off talking about, optical encoders and the different types. We'll make a quick comparison to magnetic position sensors. And then we'll take a look at a typical motor application. I say typical. I don't know that there's necessarily a typical motor application, but we'll look at something that's at least as general as we can get. And then the steps, we dive into how we choose which magnetic sensor is suitable for a given application, some decisions about the target magnet, size, material, and so on, and then how we can simulate or verify the design so that we can see, do we have enough magnetic field and are we in a good position? At the end, I'll leave some time for questions and answers. So let's dive in. To start, we're going to talk about, like I said, types of optical encoders. So here's a basic optical encoder. This consists of a code wheel, a housing, and you can kind of see there's a set screw here that's to set the code wheel to the shaft, and then the code wheel sandwiched by this kind of plastic housing that would contain an LED or a VCSEL, some type of light emitting, usually an LED for this type of encoder. And on the other side then is a photo receiver. And that code wheel, that code disk, is going to look something like one of these. Most commonly, it's going to look like something like this or like this. Up here, I show incremental encoders. So very simple. This is one of the most common type of encoder tracks in the world. It is a so-called quadrature output. You have an A track and a B track, and then a third track, which is an index. This actually requires 3 LEDs and 3 photo receivers, so 1 for each track. And the idea here, why we would need 3 tracks, is that as you're rotating, as the light alternately transmits or is blocked by the clear or black stripe, you can tell how fast the thing is rotating, but we need a second track so that we know what direction, because if you were to use something like this unencoded, if you reverse the direction, you still just see a pulse train that looks like this. Looks identical whether you're rotating clockwise or counterclockwise. So we do these 2 tracks, and then we put an index track in, usually so that you can at least dead reckon once per turn, once per full revolution, you at least know where your 0 is at. The problem here is that we don't know where we're at any other time. We're keeping count, but let's say the power goes out or we turn that off and then the thing rotates. And then we end up, I don't know, let's say here, we turn the power back on. We don't know where we're at until we get back to this index pulse. And so to solve that problem, encoder manufacturers have come up with these absolute, so-called absolute encoders. So here, there's a unique position or a unique output for each little position. So if we assume that the transmissive parts are 1s, you have a 1, 1, 1, 1, 1, 1, 0, 0. And then if you turn a little bit, it'll change. That's an 8-bit encoder. And the issue here is that if you've got these 8 tracks for just 8 bits, which isn't much, by the way, that's not a very high resolution, but those 8 tracks and 8 bits, we're going to require 8 LED receiver pairs. And the higher the resolution, the more tracks we need, and the more LED receiver pairs we need. So the cost scales with the resolution. And we'll see that. So I actually just went through on DigiKey and just basically looked at what do they have. I looked at their most expensive encoder that they sell, which is this nice, I don't even know who makes it, but it's a $979 encoder. So if you got $1,000 burning a hole in your pocket and you're looking for a nice encoder, here you go. and then down to the least expensive one that I could find, which is $21. Now, to be fair, these are single piece prices. This is not volume pricing. I just did, basic survey. $1,000, we're not really paying for the encoder itself. We're paying, this is a 400G shock, 20G vibration, unbreakable code disk, IP67, no dust, no dirt, no moisture can get in here. All right, so that's a little unfair. We're not paying for the encoder here. We're paying for something that, other than sitting in the middle of a nuclear blast, will survive just about anything that you could throw at it. This one's a little more reasonable, $114. For $114, you get 10,000 lines, which is 40,000 counts. So this is an incremental encoder, but a very high resolution incremental encoder. 40,000 counts is very nice. That is, whatever log 2 of 40,000 is, that's how many bits of resolution. So it's somewhere around 12, 14, 16, 18 bits, I think. So anyways, nice, but pricey. Here's very similar to the one that we were just looking at. These are, by the way, have plastic enclosures. On the previous page, we were looking at something very, very similar to this. So for $56, you get 1024 counts. An optical solution could easily do this. We have optical solutions that can do 4,096 counts, so an extra 2 bits over this. And for $21, we can get this part that is only 24 pulses per revolution, but it doesn't even have bearings or anything. It slides, only got a 3 million cycle life. So you can see you're paying a decent amount of money. I would consider this relatively expensive for not that much resolution. If we compare this to what we can do in a magnetic encoder, we can do about 15 to 16 bits today in magnetics, and that's without playing any magnet tricks. And I'll talk a little bit about that, doing multi-pole pair magnets later on in the presentation. But intrinsically, we're at about 15 to 16 bits with our kind of Mercedes magnetic encoder. Optical, I've seen optical encoders that go up 25, 26 bits. Expensive, yes, very expensive, but they can do it. Accuracy, also known as INL, integral nonlinearity, that is not an issue for optical. Generally the resolution is the, let's say, bottleneck. It's the part that limits the performance of the encoder, whereas the INL, because the stripes are photolithography onto the code disk, you can get almost 0 INL. In a magnetic encoder, we're going to be at about 0.6 degrees of INL, uncalibrated. We can get down to less than 0.1 when we're calibrated. So not normally an issue, but it is, I'm trying to be fair when I make the comparison here. And now we get into the stuff. This is where magnetic's going to start to shine. So size of an optical encoder, they come in all different shapes and sizes. I said 30 by 30 to 100 by 100 millimeter. Yeah, that's a reasonable size of an encoder. Our magnetic encoders are 3 by 3 and 2 by 2. They're QFN packages, 3 by 3 millimeter, 2 by 2 millimeter QFN packages. Cost, I'm trying to be really fair. Like I said, on the DigiKey survey I did, those are single piece prices. I think you can get in volume from some very low end encoders for probably $6, maybe even $5. For a magnetic, it's going to be $1 to $2. That's the sensor and the magnet included, the entire solution. So you're going to save an awful lot of money over the life of the project. And like I said, and like Kelly said, the cost is up front. You got to put some engineering work in, but that's all right. We're engineers. That's what we do. And this is what this webinar is all about. Flexibility is something that's not talked about. I put it in here because for me, as someone who's worked with these a lot, this is one of, it's a hidden but major advantage. In an optical encoder, you're going to have a module that you put on the end of the shaft, you screw it in, and then screw the housing to the shaft. There's really no flexibility. If you want flexibility with an optical, you're going to have to go get one custom designed. And again, that's going to cost a lot of money. With magnetics, we have a lot of flexibility, mechanically, magnetically, electrically. there are many, many degrees of freedom that we can play with to optimize a design. And I really feel like this is one of the biggest advantages of magnetic, besides cost. And then output, we talked about incremental or absolute when we talked about the optical. Our magnetic sensors are always absolute output. And then you can also get, so over the SPI, you get an absolute angle. And then you can also get other outputs like PWM. We can emulate A quad B to replace an optical encoder directly. We can do SSI. There's a lot of various outputs that we can use, but it's always an absolute solution. Okay, so we talked about how optical encoders work, the fact that there's these stripes and light alternately transmits or is blocked by the stripes. I'm going to give you a basic operation principle of a magnetic encoder, and it is completely contactless. We rely on the magnetic field here, this vector field that comes along with any magnet. So here I've got, and this is arbitrary, but it's a ring magnet. It could be a disc magnet. You'll see essentially the same kind of a field. So I've got my dipole ring magnet here, and then this green is going to represent our sensor. The sensitive spot, at least for MPS, our sensors is always in the direct center of the sensor. So right here is the sensitive spot. And you can see that this magnetic field, by convention, we go north pole, the field comes around and comes back to the south pole. This is, if you remember in elementary or junior high school, doing putting a magnet on a bunch of iron filings and they line up. This is how they would line up with this magnetic field. And our sensor, which is sensitive in the plane of the sensor, it's not sensitive in and out of the screen, but it's sensitive in these directions, sees the magnetic field pointing to the right and reports that. So we'll call that 0 degrees. As we rotate, the magnetic field rotates with the magnet, and now we sense, you can kind of see this vector going from the center up to the top right corner. We see that 45 degrees. So we rotated the magnet and the field rotated, and the sensor now sees that rotation happening. One thing that's interesting here, I think, it's worth pointing out, it's a little non-intuitive, is that when we are inside shaft, in other words, this is off axis, right? Our sensor is not on the axis of rotation. We could put the sensor above or below the magnet on axis, but here it's off axis. One thing that's interesting is that we are rotating the magnet clockwise, but the magnetic field is rotating counterclockwise. It's not a problem. Our sensor has a bit that you can set, and we call it the side shaft bit or the rotation direction bit. And so you flip that bit to let it know, hey, you're in side shaft, so you're going to see the opposite rotation, but report the correct rotation. And so anyways, as we rotate this thing a full 180 degrees, you can see that the field rotates, and that's how our magnetic sensor works. It's got Hall cells, or in at least one case, a TMR, tunneling magnetoresistive sensor in there that that sees and reports that field completely contactless. Okay, so we're going to look at a, let's say, typical motor application, and this is a brushless DC motor. We're looking at the back end of a brushless DC motor in a NEMA enclosure here. You can see that the back shaft, attached to the back shaft, is a code wheel or a code disc. And then this would be the sandwich part. So there's a bottom part of this underneath the wheel. Exactly what we showed before. This is an incremental encoder. The only thing about this one, and I don't know why, it has a little bit of a goofy index track with these 2 slots as opposed to 1. But in any case, if we wanted to go about shrinking this and getting a better output. So again, this is incremental. I want an absolute output. I want to have a smaller solution and a less expensive solution. The first thing I'm going to do is I'm going to remove the optical encoder, and you're going to see how awesome my Photoshop skills are. There, it's removed. All we can see is the PCB. I know you can barely tell, but yeah, that's actually just Photoshop. So so we removed the optical encoder. Now we're going to replace the code disk with a magnet. Boom, easy. Dipole magnet, north and a south. This magnet is small. It's going to cost probably around 7 cents, 5 cents, somewhere in there. And then we're going to place on this PCB that already exists. We're going to have to reroute and redo the PCB a little bit, but we're going to place our Mag Alpha magnetic encoder. And that's it. We're going to come back to this later because we'll actually look at, you know, the distance and where we place the magnet encoder and the size of the magnet material. But that's essentially a very simple replacement of a magnet. An optical with a magnet. The steps then that we have to go through, like I said, we got to figure out what kind of magnet we're going to use and the size and all that. We will get to that. One thing is there are an awful lot of magnetic encoders out there. How do we choose which one we want? And I try to boil this down to 4 basic decisions as opposed to looking at 400 part numbers and just going through the specs one by one. So let's go through like 4 basic decisions that we're going to use. The first is, do I need high resolution or bandwidth? That's a very qualitative term. To put it a little more quantitatively, high resolution is, do I need more than 12 or 13 bits? If I need to get into 14, 15 bits, I consider that high resolution. For magnetic encoders, we'll say that standard resolution is 12, 12 and a half bits, and high resolution is above that, 13, 14, 15 bits. High bandwidth, to keep it simple, if I'm trying to close a control loop with my magnetic encoder, then we'll consider that high bandwidth. And if I need that high resolution and bandwidth, I'm pretty simply going to go with the MA600. This is a TMR-based sensor. This is the part that I referred to before as the kind of Mercedes-Benz of the magnetic encoders. And it's pretty simple. If I need that high resolution bandwidth, if I'm closing a control loop, MA600. If not, I'm going to ask, okay, well, do I want low power? Am I in a application that isn't necessarily a motor here? This is going to be something like a thermostat or a door lock or a laptop computer lid, where it's going to stay in a single position for a long time until someone comes along and touches it. And it needs to be able to go to sleep because it's battery operated. If I need low power, I'm probably going to go with the MA782. That's a 2x2 millimeter package. We have a 3x3 millimeter low power, the 780. But usually if you want low power, it means you need small space also. So 782. If I don't need low power, do I need to commutate the motor? In other words, do I want to replace 3 discrete Hall cells and have my sensor output UVW? If so, it's the MA300 series. That's designed specifically to commutate brushless DC motors in 6-step commutation. If I'm not doing that, the last question is this just HMI? Is this human machine interface? Is this going to be a knob or something that someone turns and I only need low resolution and I want really, really low cost? If so, that's the MA800 series. And if not, I've got a catch-all. That's the MA700 series. So 4 basic decision points. And we can come to at least the family of parts that we need, as opposed to scanning through pages of part numbers. Once we've got a line on which sensor we're going to use, we now have to start thinking about our magnet. And there's 2 things that we need to think about with the magnet, and that is the material, the magnetic material, and the geometry, the size, essentially. So first thing, let's just do, am I going to have a basic single dipole? In other words, just a magnet with a north-south. And I drew in the magnetic moments here because sometimes I'm not a big fan of we're stuck with this old convention of north and south, but you can picture the field lines coming out. Disc or ring magnet that's a dipole has some advantages. It's really easy to simulate. In fact, you can almost do hand calculations for it. We don't have to, but we could. It can give us true absolute position. We talked about this before. If I turn this magnet 360 degrees, the magnetic field rotates also 360 degrees, and I know exactly where I'm at all times. I can turn the thing off, rotate the shaft, turn it back on, and know exactly where I'm at immediately. There's a unique field mapping to every rotational position. These things are cheap. I would expect to pay for a normal consumer industrial application with a dipole magnet. I would expect to pay certainly less than 10 cents, somewhere between 2 and 6 cents probably. And if you want to be on axis, if you want to place your sensor up here or down here, not inside shaft, then you got to have a dipole magnet. You can't do side shaft with a multi-pole magnet. So why would we do a multi-pole magnet? Well, there's reasons for that too. And this is a basic decision point. Do I want to go dipole or do I want to go multi-pole? If I go multi-pole, the biggest advantage is I get an extra bit every time I double the pole pairs. So I go from 2 pole pairs to 4 pole pairs here. Every time I rotate this 360 degrees mechanically, I see 2 full magnetic rotations. So I've got an extra bit of resolution. This is a 4 pole pair. I'm sorry. Yes, 4 pole pair, 8 pole, 4 pole pair axially magnetized magnet. And now I have 2 extra bits of resolution over a dipole. I go to 16, I get another bit, go to 32, get another bit. Now, you cannot put a sensor on axis here because, as you can see, all the fields essentially cancel out in the middle. They're axially symmetric, so there's no field in the middle. It's got to be an off axis like we showed in the motor application. If we're off axis, we can do this. The trade-off here is we can no longer achieve true absolute output because I don't know, because of the fact that I rotate 360 degrees mechanically and I get 2 magnetic rotations, I don't know which hemisphere of the magnet I'm in. So we lose our true absolute output. Gain bits, lose true absolute. That's the main trade-off. If we go to really high pole pair counts, and I've got at least one customer that's using an 82 pole pair, so 164 pole magnet, you have to get really, really close. You have to keep your air gap super small between the magnetic sensor and the magnet, because if you get away, the further away you get from the magnet, the pole pairs will tend to cancel each other out. So the general rule of thumb is I want to be closer than 1 pole pitch to the magnet for multi-pole. And when we pack that many poles into a magnet, the magnetization gets difficult. So you have to check that your supplier is able to magnetize like that and what they're going to charge you, because the magnetic setup for that is more expensive. So these are no longer a 10-cent solution. For a small magnet, you're going to be up in the 30-40 cent range. And if you're going to do something crazy like the 82 pole pair magnet, I'm guessing that's over $1, but I don't even know. And it has to be quite a large magnet. So there's some trade-offs. This is one of those levers, one of those degrees of freedoms that I talked about, where we can make a decision on dipole or multipole. All things being equal, if you get the resolution you need from a dipole, this is the easier way to go. We go dipole magnet. Without the need to talk about, or we need to make a decision on the magnet material. There are a bunch of magnet materials out there. I grade out the ones that are rarely used. Simcoe sometimes in very specific circumstances, almost never Alnico. The 3 that I see most commonly are neodymium and ferrite. And I say 3 because there's 2 types of neodymium. It's not types, but it's the way that they're built. There's sintered neodymium, which is just what you normally think of, a very brittle, but very high field strength neodymium magnet. BR here is the residual field, essentially. This is a measure of how strong the magnet is, and 1.2 to 1.4 Tesla, 1200 to 1400 millitesla for sintered neodymium. More than double what you get out of bonded neodymium, but bonded neodymium is essentially plasticized. It's a neodymium powder that's put into plastic and then or epoxy, and you can make it really cheap and into almost any shape or size that you want. the thing that you pay for is it's got the lower remnant field. And then if you want to go super inexpensive, and this stuff you could do for less than a cent. I mean, this is really, really inexpensive. So if you're in consumer and you're building 10 million of something and half a penny counts, then maybe you go with molded ferrite. Very, very inexpensive, but very, very low field. And the way you deal with low field is you need smaller air gap between the magnet and the sensor, because remember the field drops off with the square, or a larger magnet to create more field. And that's what we're going to kind of talk about in about 2 slides. Last thing, once we decide a magnet material and shape, we got to figure out how we're going to attach it to the rotating shaft. Actually, not that hard at all. The most common method by far is just to epoxy it on. We could press fit it, especially ring magnets around the shaft. That's one of the reasons that people use ring magnets, is to press fit them around the shaft. You normally, well, not normally, you would never do that with just neodymium. It's going to be for bonded, some type of bonded magnet that can handle that stress. Regular neodymium would just crack and shatter if you tried to do that. But you could do it with a coupling. That could be a disc magnet, and then you use an aluminum coupling to the shaft, or a magnetic assembly. Almost all the magnet manufacturers I work with now will make a magnetic assembly. So you could have your neodymium ring magnet with a brass bushing on the inside that the magnet supplier will build for you, and then you can press on, because that brass is nice and soft, and so it'll press fit on without cracking the neodymium material. So there's lots of options for attaching. Epoxy is probably the most common, and is, it's straightforward. And then we talked a little bit about, hey, are we going to be on shaft, side shaft? We can even do this side shaft orthogonal. Interesting. I told you that we're sensitive in the plane of the IC, and you would think that, hey, the field here is going through the part that's not sensitive, but yeah, there are fringing fields and we still get a rotation. So we can do any of these: into shaft, side shaft, orthogonal. Easiest right here, second easiest, and then third. But mechanically, another degree of freedom that we can play with. Okay, now we got to start talking about actual distances. So size of the magnet, and then distance where the IC is placed. If it's placed in side shaft, for example, we have a radial degree of freedom. We can move it out and in, and we have an axial degree of freedom. We can move it up and down. End of shaft, we only have an axial degree of freedom, up and down, but we're going to explore those. And the first thing that we're going to do to explore those is come up with some quick conventions for coordinate system, because things can get confusing if we don't have some rules. So the first rule that we're going to have is that we have an axial field, the axial component of the field. Remember, any vector you can break down into its 3 orthogonal components, and these are the 3 orthogonal components. There's an axial component that the sensor does not sense that axial component, but it's still important to understand that it's there, and we're going to call that either BZ or B axial. Then we've got a tangential component and a radial component. So one that's going out radially away from the center of the magnet, and one that's tangential to the diameter of the magnet. And those we're going to call BT and BR to avoid confusion. That way you don't have to remember what BX and BY are. In fact, I don't know, sometimes I may even say BX is radial and BY is tangential. I just don't use BX and BY. I use BT for tangential, BR for radial. And that way I'm always certain, if I rotate the sensor around here, radial is still this direction, tangential is still this direction. So that's important to know and to remember when we utilize some of the tools that we're going to utilize to now figure out where exactly are we going to place the sensor. All right, love this slide. Application notes. Whew. A lot going on here. I'm not going to go through this. I want to show you the type of things that you will find in our application notes. A lot of tables, a lot of graphs. This reminds me of my grandfather's old engineering books. This is how engineering used to be done, really, is you'd have drawings, and not computer generated ones, hand-drawn drawings and tables, and you'd have to go through and figure out, okay, let's see, I've got a diameter here and my height's here, so I want to be, this is a lot. I don't look at these application notes anymore. I don't use them anymore. The most interesting thing I think about our application notes is you can build a little bit of intuition. And I'll use this diagram as an example. This shows the ISO field line. So this shows the ISO field strengths, I should say, of a standard disk magnet. And you can see where really what this tells me is where not to place the IC. I don't want to place this sensor here or here or here or here. If I was looking to place a sensor right on axis, I get a lot of field strength. If I'm off axis, if I want to be out here, right in the axial center is the most, and I can even move up and down a little bit from the axial center. But if I get to here, man, that field drops off really fast. So I want to avoid these kind of corners. So that's what I use the application notes for now, is to kind of look at them and build some intuition. But I never go through a design and say, okay, let's look at this table and let's figure out. Don't need to, because I've got a better tool. I've got a simulation tool, and this is accessible to anybody. This is our MPS online tool, sensors.monolithicpower.com. And this thing is awesome. It is not finite element. It's an analytical tool, but you choose, hey, where do I want to place? We're actually going to use this in a couple slides. Let me go through a couple more tools, and then we're going to actually take that design that we looked at, the typical motor design, and implement it using the MPS online simulation. I get asked about this a lot. What about FEA or FEM, finite element analysis, finite element method? I use it. We have a license, and we use finite element sometimes, usually only when there's some kind of high permeability material nearby, or if the target magnet doesn't have symmetry, which is really, really rare. Normally we're using disks and rings, which is, I don't really recommend finite element method because, first of all, if you don't already have the software, you don't want to spend the money and do it just for a magnetic design. If you're designing motors and you've already got it, you're already good with it, hey, knock yourself out. The other thing with finite element is that the results are highly dependent on optimized mesh, proper boundary conditions, the correct problem definition. It's really easy to get a major screw up with a relatively minor error in your boundary conditions, for example. And in the end, every time I do it, I end up having to verify with real measurements anyways. So I just skip to the real measurements. These are the real measurements. We have these setups here in both in Switzerland, and I have one here in my lab. Like my old college professor said, the universe is the best physics simulator. Unlimited bandwidth, it's super fast, it's always right. You don't have to worry about boundary conditions. And then I just think this is funny. I found this from Scientific American back in 2020. Do we live in a simulation? Chances are about 50-50. So maybe we're already in a simulation anyways. Let's use it to the best of our ability. This is something that we can do. If you've got a design and it gets complex and we feel like, hey, we want to run beyond just the MPS online analytics simulator, I can throw your design on our test stand. This is a precision rotator. Here we're looking at one. This is someone that's trying to do direct rotor sensing. They're trying to sense the rotor with no target magnet directly. And so we have a precision rotator, a 3D magnetic field sensor, and then a precision XYZ. And we run actual tests and see what it looks like. But for now, we're going to go back to our magnetic design tool, and we're going to revisit our sample here. And the thing that we're going to do, these are arbitrary numbers. I said, hey, let's put a magnet on here and let's put an IC, and this is what I'm going to use. I literally did not do, I just kind of eyeballed this and said, this is a good starting point. So 4 millimeter inner diameter for this shaft, 10 millimeter OD for the magnet, so that we don't have, so we get some thickness in the magnet, some material in there, and then a height of the magnet of 3 millimeters. So we're going to do a 10 millimeter OD, 4 millimeter ID, 3 millimeter height. And then I'm going to place the sensor so the axial distance is -3 millimeters. And the question obvious question is why. When we make our placements, we're assuming that 0, 0, 0 on our coordinate system is the center of the magnet radially and axially. This magnet has to sit above the PCB, and it's 3 millimeters high, we said. So 1.5 millimeters is the bottom half of the magnet. And then I want another 1.5 millimeters for some clearance to the PCB, so we don't, have tolerance stack ups that make us scrape the magnet on the PCB. So I just said minus 3 millimeter. I said minus because the sensor will be below the bottom of the magnet. It doesn't matter. It's symmetric. So I could say plus 3 and it would be the exact same thing, but I'm trying to be correct here. So minus 3 and radial distance, radial out here. Well, we said we're going to have a 10 millimeter magnet, so 5 millimeter radius. And I'm just going to place the sensor right underneath this edge of the magnet. So I said we're going to go out radially 5 millimeter, and we'll use neodymium just for high strength. All right, so let's see if this works. I'm going to try to switch my screen to here, and we're going to go to our online simulator. Let's see. Oh, there's the do we live in a simulation? All right, so I'm on sensors.monolithicpower.com. Hopefully everyone can see this. Somebody say something. Oh, nope, everybody cannot, I don't think. I am screen sharing. Okay, hopefully everyone can see this. If not, Kelly, yell at me.
We can see it. Looks good. Proceed.
Okay, good. So first thing we're going to do is this simulator is going to ask us, we want to be end of shaft, side shaft, or side shaft orthogonal. We're in side shaft, right? We have our magnet and our PCBs already set, so we're going to be in side shaft. And then what kind of magnet do we want? I think we chose a cylinder with a hole, so we're going to do that. Boom. And 1.2. Oh, okay. So here's an interesting one. BREM. You don't have to memorize all of the remnant fields for different magnets. Up here, don't know the remnants of your magnet? We can click on something. If I decided ferrite, it's going to say, here you go, 0.385. But we said centered neodymium, which is 1.2 Tesla. I chose a 3 millimeter height, so we're going to go 3 millimeters, an OD of 10 millimeters, and an ID of 4 millimeters, I think is what we said. Mag alpha part number. Okay. I don't have to choose one because I'm just looking for magnetic field strength. But in this case, let's say I want to 6-step commutate this motor. So I'm going to choose the MA302 as one of the ones. And then it comes up with this filter cutoff frequency. Don't even worry about it. I can't change it anyways. So I'm not worried about that. The distance between the sensor and the magnet, center to center. So we said we're going to go R of 5, which is already in there, and a Z of -3. So put that in there. And then there's all these advanced parameters. Not going to worry about these today. This is so that after you come up with a design, you can actually go in and say, hey, here's what my mechanical engineer told me. Rarely have I met a mechanical engineer who will give you a tolerance of 0.0 millimeters. There's going to be a tolerance stack up. You can enter in those tolerance stack ups and possible angular stack ups and find out what the worst case error is going to be based on those things, but we're not going to cover that today. It's just a cool part of the tool. We're going to skip past it and launch our simulation. Oh, all right. I got a warning. Current value of the B field is 19.2, which is below the minimum recommended value of 30. And I can see that my radial field, never gets up above 20. It maxes out at 19.2. All right, so that's a problem. I chose poorly, as Indiana Jones would say, but that's okay. Let's figure out why. I want to go back to parameters here, and now I'm going to scan. This is find the best position for this sensor. I'm going to do this, and I'm actually going to scan over R. Z is set. Unless we move our PCB up or down or we change our magnet around, but let's scan over R, and we're going to start at 3 millimeters, and we'll go all the way out to 10 millimeters. And I say that because we can scan, or I shouldn't say we can scan, but look, this PCB, we have plenty of room to radially move out, right? We can move all the way out here, assuming we lay out our PCB. So we have plenty of room, and we could even move in a little bit under the magnet if we wanted to. So anyways, we're gonna do that. We're gonna see what happens if we move around radially. And so I'm gonna scan that radius from 3 millimeters to 10 millimeters. I'm just gonna adjust the step size so we don't sit and watch the computer. We could do 0.1 millimeter step size, but it will take a long time. If I go 0.5, this should be pretty quick. Launch it again. Aha. We can see what happened here. So this is the radial field, and this is the max tangential field. And this is starting at 3 millimeters and going all the way out to 10. I was here before. I was at 5. Look at this dip. Remember, I showed you on the application note, we don't want to be right off the corner of the magnet. And that's exactly where I was at. I was off the corner of the magnet, right in this dip. So what looks like if we come out here somewhere to 6.5, 7 millimeters even, we're in great shape. I'm going to go 7 millimeters. And I should get at least 42 millitesla, which is plenty. So let's go back here. I'm not going to scan this time. I'm just going to set R to 7 millimeters. And skip all this fun stuff. Launch it. And here we go. So we are at 43 millitesla. Good field. This is now a scan of the radial component and tangential component of the field as we rotate from 0 to 360. Notice that the radial field peaks out a little higher than the tangential field. We'll get to that in a second. Because that happens, this blue shows this kind of second harmonic error. You get this wavy error. That is caused by the fact that these peaks aren't equal. Means that the field is exhibiting ellipticity. It's not a perfect circle. It looks like an ellipse. We are going to take a look at how we can fix that, and it's not hard at all. Let's see here, screen 2, share, and back to my PowerPoint. When we're off axis, we're going to get this ellipticity, and it comes from this. So again, here, this shows another example that's almost the exact same. My radial field peaks out at 100. My tangential field peaks out at 50. And it happens because as I rotate my magnet, the tangential field just never gets quite as high as the radial field. You can see the two components moving, but they don't get, the tangential is never as strong as the radial. And that's very, very common in side shaft with the dipole magnet. We are going to use a register in the mag alpha called the BCT register, bias current trimming. And what it does is essentially reduces BR down to the same maximum as BT. So we're going to, since BT is 50 here, K, max BR over BT is 2. We're going to move BR down to 50 as well. And then BCT, what we're going to put in the register is 258 times 1 minus 1 over K. All right, that's a lot of stuff. We don't have to do that. We don't have to worry about going over the that math. What we can do instead is use our simulator. It's going to tell us immediately, hey, BCT should be 42. If you enter 42 into the BCT register, you're going to get this nice flat measured angle with BCT red, which is, it's an optical illusion. It actually doesn't look, it's completely straight. The red is completely straight. The blue has the second harmonic. And so if the simulator does it for us, it tells us, hey, BCT. By the way, if you want to know more about this stuff, hey, BCT, if I click on it down at the bottom, it's going to tell you BCT, bias current trimming, and this is how it works. It's really cool. I mean, this simulator is pretty sweet, I must say. All right. So let's go back real quick. We're almost to the end here. Back to screen 2. And we can calculate BCT if we want to. Let's let the simulator do it for us. Last thing. So we're essentially done now, by the way. We've figured out a good position for the sensor. We figured out a size and placement of the magnet. We didn't even need to call the FAE at MPS TED, but we can certainly do that if we run into any issues. And now we're looking like all these different part numbers. Like I told you, there's a bunch of part numbers. I want to go back and remember that with all these part numbers, I don't want you to look at this and then go, whoa, MA600. This is the one that's our newest, highest resolution, highest bandwidth. This is the part you're going to use if you want high resolution, high bandwidth. If you are closing a control loop, MA600 is for you. 732, programmable resolution and bandwidth. It's a superset of all MA7XX. In other words, any of the 704, 730, 710, 702 can be, the 732 can be programmed like that. So you could take this, evaluate it, and then later we could say, oh, you know what? Let's just use a 704. It's a little less expensive. You had this configured that way anyways, and it's literally a drop-in. All those parts are completely dropped in. The only difference is how the filtering is configured. We got our 780, the low power, wake on change, and we've got our 330, which is like the 732, but remember it can do the block commutation for brushless DC motors. So here's the actual, you know, much less overwhelming list of parts or families. And this is what I would encourage you to look at to start here. And we can dive into further details. But this is the starting point for sure. Yeah, that I'm a little over time, I think, but that's the basic presentation. The idea here is we're trying to reduce size and cost. We're trying to increase robustness. You know, one thing I don't think I mentioned, if you get dirt or dust or grease in one of these code wheels, it's done. It's going to skip counts. You can submerge this thing in oil, grease, dust, whatever, and it's got no issue. So we're increasing robustness. And then we're really increasing functionality as well, because not only can we do incremental and absolute and PWM and UVW and SSI, we're just very, very flexible, and we have lots of potential outputs. So that, I think, wraps it up for me. If we have any questions, I will take those now. Let's see. I think the questions go through the chat, right, Kelly?
Yeah, great. Thanks, Ted. A lot of good information today. So once again, yeah, if you mouse over the Zoom webinar interface, you'll see a Q&A button. Click on that and just type in your questions. And the one question we always get, even though I led off with it, is this presentation going to be available? So yes, we're recording this. We'll have the materials available. You can always go to monolithicpower.com/webinars to see all of our past efforts, and then we will email you out. It usually takes us a couple days to process it, and then we'll get it out to you. All right, I do see a question here. It says, about magnetic sensor INL and resolution limit, how can it be improved or extended?
Yep, great question. So we're talking about two different things. INL and resolution, I'm gonna tackle them separately. So resolution, the way it can be improved and extended is using the multiple magnet. So resolution is every time we double the pole pairs in a multi-pole magnet, we will increase the resolution by 1 bit. If you are looking to maximize resolution, start off with the MA600, which can already go up to about 15.5 bits. And then you can play with the magnet and start doubling pole pairs and get more and more resolution. In Hall-based encoders and Hall-based position sensors, there is a trade-off intrinsically, and I didn't go into this because it gets deep, but there's a trade-off between the bandwidth. So we talk about this filtering and bandwidth. There's a trade-off between bandwidth and resolution. In Hall, we're going to peak out at about 12 bits. You can eke out another 2 bits, but the bandwidth starts to get really, really low, and that's because we're filtering. Halls have a lot of white noise, and we can filter that white noise and keep extending the size of our window filter, but it creates a very slow step response. And so that's how those are the trade-offs. That's how we improve INL. I'm sorry, resolution. Because the MA600 is TMR, it has an intrinsic high resolution in the front end. In fact, I expect that in the next year or two, we will increase the intrinsic INL of the MA600 by even another 2 to 3 bits without touching the bandwidth. And then beyond that, we're looking at other technologies. We're always looking at other sensing technologies. So that covers the resolution. INL is a separate thing. INL is something that, again, TMR has just intrinsically less INL, 0.6 degrees over temperature. It's because TMR has a lower temperature drift than Hall does. 0.6 over temperature is what you're going to get. It's about the best you're going to get. It's going to be about 0.8 for Hall until you do calibration. If you would like to do calibration, and for Hall, our Hall-based sensors, you'd have to do that externally. For our MA600, it has calibration tables built into it. So you can run it in situ and calibrate it. And that's where you can get less than 0.1 degrees of INL. And so that's how we can improve the INL.
Great, thanks, Ted.
Sure.
I'm sorry, did you have more?
No, I was just seeing the other questions, but you can read them and I'll answer them.
Yeah, so next one up is the difference between TMR and Hall in terms of external field sensitivity.
Yeah. The one line answer is that TMR is significantly more sensitive than Hall. The longer answer is that Hall will work down to 10 or 15 millitesla, but you will see a drop off from about 40 to 50 millitesla as you go down from 40 to 50 millitesla down to 10 or 15 millitesla. You will watch the resolution start to fall off, and it falls off not linearly. The difference between 40 millitesla and 30 millitesla might be 0.2 bits, and then from 30 to 20 it might be 0.8 bits, and then from 20 to 15 it's like a bit and a half. So it really starts to fall off. TMR does not exhibit that. TMR will work until it just doesn't. And so it has the resolution doesn't go anywhere, doesn't go anywhere. Then you get down to around 10 millitesla or so, and it falls off a cliff. So that's kind of the difference. We can make TMR more sensitive, but there are other major trade-offs, and in our part it's not done. In our part, it's going to fall off at about 10 millitesla.
All right, next one up, the encoder misalignment correction, the BCT register, is available for the on-axis encoders too, or only for the off-axis ones? And then is there an automatic procedure or software that MPS provides for the BCT correction calculation?
Yes. Okay. So we don't need BCT for on-axis. When we're on-axis, there's no ellipticity. The only time that I would ever think to use BCT on axis is if you've got a really high mechanical tolerance stack up and you want to, so let's say you're making 1,000 widgets, and you are going to, at the end of line, you're going to calibrate each one, and you have a pretty significant difference in, you're not really on axis because your radial tolerance stack up is huge. Then you could use that BCT register to correct those radial mechanical errors when you're on axis, but generally it's not needed. Generally, when you're on axis, we're pretty tolerant to radial displacement as well for what I call a standard mechanical tolerance, which is 0.3, 0.5 millimeters. And then the second question is there an automatic procedure or software that we provide for the BCT correction calculation? So yeah, there's two things that we can do. One is we have our simulation software, which will tell you the nominal value. But if you would like to calibrate each individual one, which I do have customers that do that because they want, it's exactly the case that I just said. They want to, at the end of line, calibrate each individual We have our Macom software. It is our standard test software in a kit that is essentially translates from our SPI bus to USB and then our graphical user interface. You can find that on our website. And that kit, there's not an automatic way to do BCT, but essentially the procedure, and I can go over this in much more detail, Paul, if you know, offline or later, but to give you the basics, you can adjust BCT and watch the second harmonic error. If you're running a motor at a set RPM, and we want it to be a high enough RPM that it overcomes speed ripple. So you know, and sometimes maybe even add a flywheel on there so that there's not speed ripple. But if we can set it to a constant RPM and then adjust BCT until we minimize the second harmonic error, which is something that our application will show you is the second harmonic error, then that is the ideal BCT. So that's the way that we and that can be even more automated, but it's not included right now in our software. Oh, and again, I'm happy to talk to you, Paul, more about that via email or whatever makes sense.
All right. Next up, what would you recommend for applications where you need to sense mid-shaft, the ends of shafts are not available for mounting, and the run out of the shaft cannot be very tightly controlled, like a drive shaft?
Yeah. We have these applications. The best way to do it is a standard side shaft, right? So you're in mid shaft, get a ring magnet that goes around the shaft. Hopefully you can press the magnet all the way down around. If not, there are options to get two magnetized halves and actually put them together. You're going to run into some nonlinearity when you do that. And so I'd recommend that you have to calibrate if you're taking two hemispheres and putting them together around the shaft. If you can get a single ring and push it all the way down to the middle of the shaft, that's much better. In any case, then you're going to be in side shaft, standard side shaft, preferably axially centered on the magnet, and you should be in relatively good shape.
All right. Next up, and looks like we're getting to our last one. So if you do have more, chime in now. Let's see. So this one is the sensitivity to external fields dependent on the sensor position, on axis or off axis?
In general, yes, because the sensitivity to an external field is directly proportional to the field strength that we're seeing at the sensitive part of the sensor. And when we're on axis, oh man, my Wednesday, I apologize, guys. Wednesday at noon, they test the tornado alarms. So anyhow, I'll try to keep the microphone close to me.
We can't even hear it.
Oh, really? Okay, good. That's it's bad webinar policy. Anyways, so when you are on axis, you can almost always get higher magnetic field strength than when you're off axis. And the sensitivity to an external field is relatively easy to calculate. You figure out what your external field is, place it orthogonal to the target field, and then you can see what the deflection would be. When you're on axis, and I didn't show this, but if you go onto our simulator, you can see what's called a biaxial magnet. It's also a dipole, but it's axially magnetized. One hemisphere is axially magnetized up, one is axially magnetized down. You get a very, very strong field close to the magnet, and it drops off really fast. The problem when you're in side shaft is you always have to BCT, you have to reduce the larger field down to the smaller field, and so you almost always end up with a weaker field in side shaft, and so that means a relatively higher effect of an external field.
All right, and we did have another one come in. Is it possible to realize R equal 80 millimeter, or will the magnet cost explode?
So the easiest way to estimate magnet cost is especially when I'm dealing with neodymium, is I just estimate how much material. So 80 millimeters in neo, in sintered neo, is going to be freaking expensive. It's a commodity thing, and it's literally just how much material. And 80 millimeters is a lot of magnet material. The good news is, if you're at an 80 millimeter radius, that's a big magnet. So you can probably use a very weak magnetic material. Bonded sintered isn't even that weak, but you could even go to, plastoferrite, which is very, very inexpensive, and it's weak, but you have so much of it that you'll probably be fine. And 80 millimeters in bonded ferrite is not going to be expensive. I mean, bonded ferrite is, you can estimate that you're going to pay about what you would pay for the same piece of just straight up molded plastic. So it's not expensive at all. I would just definitely stay away from neodymium if I was doing that.
All right. That looks like the last one. So type now if you got any left. Thanks everyone for bearing with us today. Lots of good stuff coming in. You can see Ted's got his email address up there. So if you do have any additional questions or need input on your project,
on any of the questions, yeah, feel free to email me. I enjoy talking about this stuff, so I'm happy to do it.
I think Ted just likes talking, but
correct.
Anyway, thank you for your time today. Oh no, we got another one in right at the buzzer.
Larger ferrite magnet have better tolerance rejection than the small neo. Yes. So sorry, I should answer this I should read this for everybody. Would a larger ferrite magnet have better tolerance rejection than a small neodymium magnet? And the answer is yes. Larger magnet has, all things being equal, a larger magnet will always tolerate more positional inaccuracy than a smaller magnet. So if you can afford it in terms of space, larger ferrite's probably even going to be cheaper than a small neo anyways. So when I say afford it, I mean, if you can afford the space that it takes up, then yeah, it will reject tolerances better than a small neo.
Great. And other than a couple of thank yous, thank you back to you guys as well. I think that will conclude it for today. All right. Thanks again. We'll be sure to send out all the materials and the recording of the session by the end of the week. Bye, everyone.
Bye, thanks.